Welcome everybody to today's seminar. Our speaker today is Wenwen Lee, and she will talk to us about two-parameter persistent homology of the second configuration spaces of star graphs.
Thank you for inviting me. It's my pleasure to give a talk at AATRN network. So this is a joint work with my PhD advisor Murad Ozaydin. So let's get started. Let's see. Okay, so here's a big picture of my talk. So just consider there are like endpoints in a metric space. And we have some proximity restraints between each pair of xi and xj, such as the minimal distance allowed between them is some positive real number. So in this talk, we just treat those points as robots. And so we consider the space that consists of all such possible arrangement of those n robots in this metric space X. So the question we're trying to answer is that how does this restricted coherent space, or like in particular its homology group, change when we change this proximity restraints or the space? So in this talk, we will focus on case that n equals to 2. In other words, we'll only have two robots and X. So the metric space is the geometric realization of a star graph. Oh, by the way, so if you have any questions, just feel free to stop me during my talk. Okay. Yeah. So here's a setup. So let gamma be a finite connected graph, and we let X be the geometric realization of this graph, gamma. And we assign a positive number for each edge for this graph, that this number will represent the length of the edge. And after that, so X has a metric delta. So in particular, this means for any pair of points X and Y in this space, delta XY is the length of the shortest path between X and Y. So we use X sub L to denote this metric space X delta. So now we're ready to define the nth coherent space of this metric graph. So now when we have a parameter, this is vector R and edge length vector L, then the nth coherent space of X with those parameters is a collection of n tuples lives in this product space, such that the distance between X and Xj is greater than or equals to Rij for each pair of I and J. So if this if the edge length vector L is fixed, then we just omit this symbol, and we use Xn sub R to represent this nth coherent space of X with those two parameters. So yeah, so here are some technicality. So first of all, so we allow gamma to have multiple edges. However, if gamma has loops, then we add one vertex to subdivide the loop into two edges. And after that, we can just assume that X, which is the geometric realization of the graph, it has the regular CW complex structure. So the reason that we want this is because a regular CW complex is completely determined by its phase pole set. And so the maximum cells of a regular cell structure for the nth coherent space, with the restraint parameter R, are obtained by intersecting the space with the maximum cells of the product space of X, which is also regular. And so if Xn sub R and Xn sub S, they have the same combinatorial type, then actually they're homomorphic to each other. So we have an equivalence relation. So here's a remark. So when R is small, then this nth coherent space with restraint parameter R is actually homotopic equivalent to the nth coherent space of X. Okay, so let me move on. So there's a way to characterize the cell structure of the second configuration space of metric graph with restraint parameter R. So because here we only have two robots, so we can just consider this by like case by case. So there are two scenarios. The first scenario is those two robots actually they're on the same edge. So we can use an inequality system to describe this picture. And so we got this, so inequality system on the right. So for example, the first two like inequalities. So this basically says this green robot is on this edge, similar for those two like inequality. And for the fifth inequality, this just says, so the distance between x and y is, So x minus y is less than or equal to 0. So this means x is closer to the left end of this arrow compared to this purple robots. And this inequality says x minus y less than or equal to negative r. This means that, so the distance between this green robot and purple robot is at least r. Yeah, so let me move on. So because we have this inequality system and we only have two variables, we can draw the solution space for this inequality system. And this is what we did. And so actually, so this shaded area is a cell for this restricted second configuration space. Okay, so this is a cell. Here's another scenario. So this is when those two robots they're actually on different edges, and we can do the same trick, right? So we write it down the inequality system, and so solution space will give us the cell of this case. And so for example, so this is a cell for the second configuration space with the restraint parameter R. Okay. So we are going to use this cell structure later in my talk. Yeah, so that's a lot of definitions. So let's do a quick example. So in this example, so we consider two robots moving on a Y-shaped rail. Okay, so here are two parameters that we will considering like in this talk. So the first parameter is the minimal distance allowed between those two robots, so which is R, and the other parameter is the length of the edge E1. Okay, so we denote this parameter by L. However, so the length of edge E2 and the length of edge E3 they are fixed, and they are all equal to 1. Okay. So now, so let's just choose different value for the length of edge E1 and change the parameter R to see what will happen. Okay, so let's choose the length of E1 to be 1. Okay, so when R equals to 2, we can actually draw the configuration space, and this is the space that consists of 6 points. Okay, so on the left, I'm tracking down the path component. So therefore, at R equals to 2, I draw 6 dots. Okay, so now let me decrease R. So R equals to 1.7. So now, so instead of 6 points, so we have a space that consists of 6 triangles. But here we still have 6 path components. Therefore, so we keep those 6 generators alive for H0. Okay, so now if we further decrease R, so as you can see, so those triangles get larger, but we still have 6 path components. However, when R equals to 1, those 6 triangles, they merge into 1 path component. So therefore, at R equals to 1, we kill 5 of the 6 generators for H0, and we keep 1 of it. So 1 of the generators are alive. Okay. So now if we further decrease R, we get smaller holes, and we also get 6 yellow-red triangles. and when r equals to 0.4 on the right-hand side, so this is configuration space, but again, we still have like one path component, so therefore, we just keep this generator alive. And at the end, we got the barcode for the zeros persistent homology of this filtration. So this is when the length of edge E1 equals to 1. Okay, so how about we choose a different value? So let's choose, so the length of edge E1 to be 2 and see what will happen. So now when r equals to 3, okay, so this configuration space is no longer empty, and the space consists of 4 points. Okay, so now let's decrease r. So when r equals 2.5, so the space consists of 4 triangles. So we keep those 4 generators for H0 alive because we still have 4 path components. However, when r equals to 2, so first of all, so you can see, so those 2 triangles, they merge into one path component, similar for those 2. So therefore, we kill 2 out of 4 generators at r equals to 2. In addition, we have 2 points born at r equals to 2. So therefore, we add 2 generators at r equals to 2 as well for H0. So now let's decreasing r. So when r equals to 1.3, we still have 4 path components. Now when r equals to 1, so the space is path connected. So therefore, we kill 3 of the 4 generators of H1. Okay, so if we further decrease r, so this is the space, and again, it is path connected. So we keep this generator alive. And if we further decrease r, at the end, we got the barcode for zeros persistent homology for this filtration. So let's recap what we did. So we actually have a bifiltration. So we did a computation, like when we fix the length of edge E1 and we vary the value for R. However, we also have the filtration going upwards, right? So if we change, so if we increase the value for for L, so we also have the inclusion map going up. So if we fix R basically, so this is the bifiltration we have for the Y graph, for the configuration space of the Y-shaped graph with 2 robots. And this is this is the functor we're considering. So so the parameters, there are piles of real numbers. So the first one is contravariant. The second one is covariant. Okay, so this can be generalized for metric graphs. So let X be a metric graph, and let R and be a restraint parameter, and L to be the edge length vector. Then we can define the nth persistent homology of this multi-filtration to be the composition of the following functors. So the first functor is the nth configuration space of metric graphs with those 2 parameters. And then if we post-compose with S homology functor with a field coefficient, then this, then we will get the nth persistent homology functor of this multi-filtration. Here, so M is the cardinality of the edge set of this graph, gamma. And here's a remark. So there is no hope to classify this S persistence module of this multi-filtration, because in fact, there's no hope to classify finally generated FXY modules. This classification problem is wild. So we have to compute the incomposable direct summon of those persistent modules one by one. Okay, so let's move on. So here's our approach. So we want to simplify the computation as much as possible, because if we go back to this by filtration, so this functor, so the indexing set is uncountable. So anyway, so let me just go through this. So we want to figure out how does the second configuration space with those two parameters change up to homotopy when we change this parameter R and the adjoint vector L. Okay, so here's a definition. So if we fix this vector L, then at certain R values, the combinatorial type of the configuration space change, and we call such R critical value for this adjoint vector L. So let me explain what does it mean. Okay, so say if we have a cell on the left, okay, then we change the R value. Okay, so now so if we increasing R, then those two lines with positive slope, they will get closer to each other, and similarly for those two lines with negative slope, they will get closer to each other. So at some R, we might get a cell on the left. In other words, those two lines, so they intersect at this vertical axis. Okay, so so in this case, so this value R is a critical value, and so the homotopy type of this nth configuration space doesn't change. However, the homeomorphism type may change. Okay, so let's see an example. So this is an example when the homotopy type doesn't change, but the homeomorphism type change, right? So we start from the space on the left, then we decreasing R, and those two lines hit at this vertical axis, and those two spaces, although they're homotopic, but they are not homomorphic to each other. Okay, so here's another scenario. So say we have a cell on the left, okay, and we have critical R values at those 2 points. So now, so if we further decrease R, again, those two lines with positive slope, they will get closer to each other, and those two lines with negative slope, they will get closer to each other. So therefore, we get a cell on the left. So in this case, so the combinatorial type of the cell actually, so they remain the same. However, so in this case, both the homomorphism type and the homotopy type of the entire cell complex of this nth configuration space may change in this case, right? So the space can get one more path component. So yeah, so this is an example. So we start from this critical position, and then we let's see. Yeah, so then we increasing R, we got smaller spaces, right? And so this space is no longer path connected. So in this case, the homomorphism type of the second configuration space change. Yeah, so let's go back to the toy example that we did earlier. So this is the second configuration space with the Y-shaped graph. So parameter is R and L here. So L is the length of edge E1. Okay, on the right-hand side, those 4 lines I highlight in black, every point along this, every point along those 4 lines is a critical value. Okay. So one thing to point out is, if you have like a pair of points like in the interior of each region, so there is no like homotopy type change between them because they actually have the same phase pole set. So therefore, they are homomorphic to each other. Okay. So now we just pick one point from each like region. I mean, so by the way, so we call those regions chambers. So we pick one point from each chamber to compute the homotopy type. And we got the picture. Right. So for example, so any point in this blue chamber, so it has homotopy type. So I mean, so it is homotopy equivalent to S1. And similarly, for any point in this yellow region, so the configuration space with the given parameter will homotopy equivalent to the space of 6 points. And now this is a bifiltration, right? And if we apply the S homology factor with the field coefficient, then we get the persistent modules. And this is what we got. So for the figure on the left, so this is the zeroth persistence homology of this bifiltration. And the figure on the right is the first persistent homology of this bifiltration. So as you can see from picture on the right, so support of pH1 of this bifiltration is an interval, and for each point in this module, we assign the ground field F. So therefore, pH1 of this bifiltration is actually an interval module. So therefore, it is indecomposable. And now we want to figure out the indecomposable direct summand of the zeroth persistence homology of this bifiltration. Okay. So there's our, here's our approach. So we associate the hyperplane arrangement with this pole set P, which can be defined as follows. Okay. So for each chamber, we assign an element of this P, and then each arrow in the Hasse diagram of this pole set P represent a wall between two chambers. Okay, and the orientation of the arrow is given by the filtration of this second configuration space. Okay, so we find out this construction gives a functor from the parameter space to this pole set P we just constructed. Yeah, so let's see a picture. Here is a picture. So so background is it's the pH0 of the second configuration space of the Y-shaped graph, right? And we assign each chamber a vertex, or so we assign each chamber an element of the pole set P, and for each arrow it represents we have so the arrow just like across the wall basically. And we got this new representation. So this is a representation from the pole set P to the category of vector space. So in other words, so we associate the zeroth persistent module of that bifiltration to this like representation with the support coming from this pole set P. And we can actually compute the indecomposable segment for this representation and then translate it back to get the indecomposable direct segment for the zeroth persistent module. And this is what we did. And so this can be generalized to an arbitrary like finite metric graph. So we found out that this functor so the f persistent homology functor of the second configuration space of a metric graph. So this functor actually factors through this poset that coming from the hyperplane arrangement, and this diagram commutes up to natural isomorphism. Okay, so let's see our computation. So just, so we use this method, then we figure out the indecomposable Dirac segment for the zeroth persistence homology of this bifiltration. So there are 5 Dirac segments. And so those two are the same, right? So those two on the bottom, they are the same. However, so the diagram on the top left, so you see we have 2 and 2 for those 2 chambers. So this means for every point in those chambers, we assign an F2, right? F cross F to the point. So therefore, the zeroth persistence homology of this bifiltration is not interval decomposable, because this module is indecomposable, but this is definitely not an interval module. Okay. So now here, so we did the computation for the second configuration space of the Y graph. But can we generalize this computation to star graphs? And so the answer is yes. Oh, so before I move, I can just come back to this if you have time. Yeah. So so a star graph is a graph that we have a vertex of degree k. Like star k graph actually. So a graph with a vertex that has degree k, and the other vertex they have degree 1. So we use star k sub L to denote the matrix star graph, where each so where this L is a vector that represent the edge length vector, right? So again, so we only consider the case that so the length of edge E2, the length of edge E3, they're all 1 except the length of edge E1. So the length of edge E1 is a parameter, and we're gonna change the value for that. And so the key observation here is, so the hyperplane arrangement, so in other words, so the critical hyperplanes for the second configuration space of the star graph and the second configuration space of the Y graph, they're actually the same. So we still have those 4 lines in the parameter space. So then, so we just compute like each point from the chamber to figure out, so the homology group for each chamber basically, and this is what we did. So we compute the zeroth persistence homology of this bifiltration coming from the second configuration space of the star K graph, and similarly the PH1, the first persistent homology group of this bifiltration. Okay, so yeah. So actually, so this result holds with integer coefficients as well. But if we use the integer coefficients, then every number in the chamber will represent the rank of the abelian group. Okay. Yeah. So yes. So from the figure on the right, so if we construct the poset P coming from PH1, then it is actually a A2 quiver, right? So we assign a point to each chamber, and we have an arrow going upwards between them. So so it is actually an A2 quiver. So therefore, it is interval decomposable. But for PH0, things might get complicated. So we do the same trick. Basically, so we assign an element for each chamber, and we figure out the arrows, between them. And then we compute the indecomposable direct summon for that poset representation, and then translate back to get the indecomposable direct summon for the zeros persistent module of this bifiltration. And we got this result here. So we figure out the indecomposable direct summon for this zeros persistent homology of the bifiltration of the second configuration space of the star K graph. And here again, so the figure on the top left, so we have 2 and 2 for those two chambers. So that indicate that for each point, we have an F2 assigned to that point. So therefore, the pH0 of this bifiltration is again not interval decomposable. However, so the pH1, it is interval decomposable, as I claimed earlier, and those are the indecomposable direct summons. Yeah. So let me go back actually. So I do want to point out that so if we take horizontal slices to each indecomposable direct summon and then combine them, then we'll get the one-dimensional barcode. And similarly, if we take the slices vertically, you will again get the barcode. Yeah, so since I still have some time, so let me actually say something more. So we did a computation, for the H graph actually as well. So so let me define the H graph first. So by H graph or generalized H graph, this is what I mean. So this is a graph that can be obtained by should I say like a wedge product of a star M graph and a star N graph. So here, so I didn't draw the actual vertex, but so this is how we compute the persistent homologies basically. So HMN is a graph like this, right? So it is a graph that here we have M-1 leaves and N-1 leaves here. So it can be obtained by take the wedge product of two star graphs. One is star M, the other one is star N. So yeah, so we do the same trick because we already have the data for the configuration space so we have the data for the second configuration space of the star graph. So we can compute the second configuration space of this HMN just using the Mayer-Variatorius special sequence argument. And this is the result. So the figure on the left is the zeros persistent homology of this bifiltration of the H graph. So the H graph is actually H3, 3. So it's a wedge product of two Y graphs. And this is the result. And the figure on the right is the first persistence homology of this bifiltration. And again, so if we assign a vertex to each chamber and an arrow between them, if there's a wall, then pH1 is again, this is an A7 quiver. So this is also interval decomposable. But pH0, we need some computation, and this is what we got. So we compute the indecomposable direct summon for the zeros persistence homology of this bifiltration. And it turns out it is interval decomposable because every chamber, so the number, is 1. So it is interval decomposable, which is amazing, right? Yeah. And I mean, so you can do the similar computation for this generalized for the second configuration space of the generalized HM graph. And so you can show so you can show that so the indecomposable Dirac summon for this zeroth precision homology is again interval decomposable, because every number that we have for each chamber is 1. So let me stop here and let me know if you have any questions. Thank you.
Thank you very much for the great talk. Before we get to questions, please, let's all unmute ourselves and clap for the speaker.
Thank you.
All right, it's time for questions. So if you have a question, please just go ahead and unmute yourself and ask the question.
I have a question. Namely, you said that it's amazing that they are interval decomposable.
Yes.
Can you explain a bit more, like why? It seems that for you it makes a big difference if they're interval decomposable or not. And can you explain a bit, like what can you do with the knowledge that they are interval decomposable, or what's the further steps? What's the amazingness about it?
Oh, yeah, that's a great question. So, I mean, so because, okay, let me go back maybe. So as you can see, this graph can be obtained. So if we let's subdivide this edge U1, then this H graph can be obtained by taking the wedge product of 2 star graphs, right? And we know the zeroth precision's homology of the second configuration space of the star graph, they are not interval decomposable. But somehow, you know, so the second configuration space of this H sub Mn, so it is related to the zeroth precision homology of the star graph. So they're related, because so if you use the Murad special sequence argument, so there are 2 covers that coming from the second configuration space of the star graph. So somehow, you know, things happens and magically, then, you know, so zeroth precision homology of this graph is interval decomposable, but the zeroth precision homology of the star graph, so it is not interval decomposable.
But maybe a further question in that direction is, should I see your research more as a good example for 2 spaces that are not interval decomposable and their wedge product is interval decomposable?
Yeah.
Or should I rather see your research as saying something about robots walking on a graph, you know?
Oh,
Or both?
okay. Sorry, sorry, I misunderstood your question. So, so the reason that we compute the second configuration space of the star graph, as well as this generalized H graph, is that so our goal is actually figure out the persistent homology of the second configuration space of the trees. And any tree can be like decomposed into like star graphs and those generalized H graphs, right? So if we have the data for each patch, then we can use the Murad special sequence argument to figure out the persistent homology of that. That's the point. Yeah.
Thank you. That was exactly what I was curious about. Thank you.
No problem.
I have a question.
Go ahead.
Well, first of all, thank you very much for the nice talk. I noticed that you only consider the analysis of persistent modules in dimension 0 and 1. And
Yes.
for the case of star graph, I would imagine that that's That's correct, because the usual configuration space of a star graph is homotopy one-dimensional. So my question is, what happens for these configuration spaces with parameters that you are considering? If you see anything, say in the case of a star graph, or even in the case of an edge graph, if you see anything in dimension 2, say if you see any homology in dimension 2.
Yeah, so that's a great question. So let's see. So we have on proposition like in our paper, that's, if I remember correctly, so all the higher homology groups of the second configuration space of trees vanish. Yeah. So let me pull that out real quick. Yeah, I mean, so I would love to talk more, but that's how I like remembered. So the second configuration space of the tree graphs, they're all zero, or even like for higher like homology groups, they're all zero.
Okay.
Yeah.
Thank you.
No problem.
Ethan, go ahead and pose your question.
Thanks. So thank you very much for the nice talk. I was wondering, have you done anything with 3 robots rather than 2? Like, for example, looking at a star with 4 spikes, and this, I guess, maybe might tie in with some of the homology. If you've got more robots running around, then there's sort of more of a chance to get sort of higher dimensional homology showing up.
Yeah, that's a great question. So this actually is my like ongoing project with my advisor, Murad Ozaydin. So the challenge of like computing those, like, I mean, like from my point of view is that if we still use the same technique, so in particular, the Mayer Veritor spectral sequence, then we'll have like more covers and it might hard to compute. So that's a challenging thing. So we are trying to find if there are like any other way to allow us to compute those configuration spaces. Yeah.
Thank you.
Henry, go ahead.
Thanks for the nice talk, Wenwen. So my question is, these computations, how much are you doing sort of by hand? I imagine probably most of the work you showed today is by hand. Is that correct or not? And then how much do you think could be done by computer, say, in the future? Like, I know the size probably grows quite large, but if you input a graph and the lengths, could you have a computer try to build the cell structure and maybe not get homotopy types, but maybe get homology groups, things like this?
That's a great question. So for the first half, I did those computation by hand, like 100%. So I'm working on like, you know, to use this computer to help us to compute with Han Qinghu. So he's a colleague of mine at Hobart and Williams Mixed colleges. But I mean, so it's tricky that, you know, to input the Mayer Veritor spectral sequence argument to computer. So as far as I know, yeah, so definitely, so we're hoping to find some, you know, like program to like, you know, to compute, because compute this by hand, it's really like difficult and like time consuming. So we hope that like, you know, to get some like program to help us to compute, so at least like the wedge sum of like like star graphs, or sorry, so the configuration space of the wedge, so wedge product of the star graphs at least. So we tried.
Very cool.
Yeah, so I mean, so we tried, and so the second, so I think like the product so if you have like two like star graph and take the wedge sum, then so I think so the output of our program like coincide with my computation with this second computer space of this generalized H graph. But we haven't tried like if we have like 3 copies of like star K graph and take the wedge sum, like what we have. We haven't tried that yet. Yeah.
Thanks.
Okay, next question is by Nyechi. Sorry, I'm not sure how to pronounce your name.
Thank you. Thank you, Wenwen, for the great talk. So I have a question on, there was a slide before where you showed different, where the lines, like the ones that have positive slope and negative slope when they're coming together, and the ones that are moving apart, and how that changes the homotopy type.
Yes, let me
Or
actually.
not.
Yeah. Go ahead.
So my question is like, I mean, you may have mentioned this in the talk, but I didn't quite get it. What motivates you considering the homotopy type, as opposed to like any other, you know, topological invariant of the space?
So here, I mean, because our goal is to figure out, you know, like the ith persistence homology of some bifiltration. So for us, so we just compute, you know, so the homotopy types, and but I'm not sure if there are other like topological invariant that we can use to make our, you know, computation easier.
So are you looking specifically maybe at pi1 or, you know, general homotopy?
Sorry, so I didn't like understand, like, so the homotopy type is just the classical definition, right?
Oh
So
my God, yes.
yeah, so we didn't use the generalized.
Yeah, thank you.
Yeah, I mean, so we can talk later. I don't think I fully understand your question. But I mean, so in short, so the homotopy type I use just the classical definition of the homotopy type.
Maybe to follow up on that question, I think
Okay.
one way, if I interpret the question correctly, then if you anyway later only care for homology, then you could already here maybe be less restrictive, like not caring about the homotopy type, but directly caring about homology. And it goes a bit in the question what Henry said before, that maybe by replacing the homotopy type by homology, it would also be easier to have it be computed by a computer instead of computing things by hand. So maybe the question goes in that direction.
That's actually makes sense, but I mean, so because we also want the indecomposable direct summon for the persistent modules. So I mean, I haven't like think about this about like a very carefully yet. But like on the top of my head, so if you like relax the restriction too much, we might like lose track of those generators for the persistent modules. I'm not sure if that makes sense.
Yeah, thank you.
Yeah.
Are there any further questions? Okay, then I will dare to ask a question. I was wondering, so you consider the star graphs where you said the zeroth homology was interval indecomposable, right? And then you
Yes.
had the H graphs where by some magic you got decomposability of the same homotopy things. So what happens if you take a Y graph and you connect, you know, like the same thing you did with an H graph. So you took like an edge and connected 2 star graphs with an edge, but then you
Yes.
could take 3 edges and then put star graphs on each of the 3 edges. What happens? Do you know what happens there, or do you have some, you know, expectations?
I don't know. because so first of all, those computations, I mean, it's complicated. Again, so as I said earlier, that so the way like we compute peer zero of those back filtrations are using the Miniature's special sequence argument. So we tried to compute some other so the configuration space of some other graphs, but it's complicated, some would say. So especially like when you do all the computation by hand. So hopefully if we can find some like program that help us to compute those homology groups at least, then we might have like a better like understanding of the persistent homology of the second configuration space of so for example this so the graph that you just described. Yeah, but currently I don't have any like computational result for that.
Yeah, that's okay. No worries. But you mentioned that this is what Teresa was asking. Why is it such an important result? And you said that you can then decompose each graph.
The tree graph into the wedge product of star graphs and the generalized H graphs.
Okay, and you cannot, I mean, am I wrong in thinking that the graph I described to you is one of those?
Yes, you're right.
Yeah.
You're definitely correct. Yes.
Okay, good. And so can you use the results that you have on H graphs and star graphs somehow, and this decomposition somehow in connection?
For the homology group computation, the answer is yes. For finding the indecomposable direct segment of the persistent modules, we need to be careful about that. Yeah.
Okay, great. Thank you very much.
Great question.
Thank you. Okay, are there any further questions? Okay, if this is not the case, then thank you again for the great talk, and I'll stop the recording.